applications. In applications of the random effect, okay, it's nice. You see, you'll be computing the fixed effect, but it's nice to have a table of the OLS, the PAUL, some of the other ones, to just do comparative analysis of them. Comparing variables is very nice. It gives you a bigger picture than just sticking to one model. Okay. So when you compare it with others, then you now make your model very, very strong. So under the final general model, okay, the general model, okay, the random effect. Remember, random effect is including everything that a fixed effect omitted is including them. Education, experience, ethnicity, all of that are being incorporated. Then, random effect becomes effective when the UI is uncorrelated with the XI. Remember that. The UI can be left inside the error term. You can leave that, leading to autocorrelation over time. It can be handled by the feasible GLS and the OLS. We've made this point already. It's just a slight repetition. The random effect allows time constant variables to appear. I've also made this point to compute. All right, so let's go and do the random effect in R. Okay. And then we'll now select which of them is appropriate as far as these variables are concerned. These very, very ones are concerned, because that's what most papers will do. So, when I needed to calculate my robust, this was a robust. Okay, so this one is WRFE. Let me just WRFE. All right. So these were the robust for the fixed effect that we left out. So I'm just doing that. Now, when you normally run it, you have to double click it to just show the robust for the newer Western, all of those things. You guys have seen this already. Now let's go and run the random effect model. This is the random effect model that I just showed you. Now let's run that, and there you go. So watch something. This is going to be interesting. You can see that the key variables are significant along the lines of the random effect, but all the time dummies are not significant. All the time, including ethnicity other, okay, they are not significant. Ethnicity other is significant. It's just the time dummies that are not significant. The 1987 time dummy was like 10% significant. So keep that in mind. Again, there's nothing good or nothing bad here. There's nothing good and nothing bad here. Look at these terminologies. We'll be talking about them pretty soon. And we spoke about the theta. By the way, this is a theta, the software. We'll speak about that series. Okay. So let me see if I can show you the results for the results that you get for the random effect. This is called one-way individual effect random model. It uses something we call Swami-Arora's transformation. There are several other transformations. You remember the transformation we dealt with? It uses similar things, but then there are several other ones. This is a complex one that you can read on your own. So the first part of the model, okay, the results shows that the data is balanced. And you can see that here. The data is balanced. The time period is 8. The sample size is 4,360. Okay. At the top of the table is called effect. So this is effect. And that's what something that you want to be able to know. Okay, so when you look at the effect, you will see idiosyncratic errors there. But let me show you this. Yeah. You see those idiosyncratic error, you see the individual specific factors. And then you have the theta also there. The time specific factors have already been included in the model. So the time dummies are included, so maybe nothing more there for it to be captured. But you have the theta, which is 64.29. Okay. If the data were balanced, okay, the values will be constant. But for unbalanced data, a summary of the values is presented in the header of the output. What is this data? What is this 64.29? What is that? Well, the data tells you the variability that will come, the variation from the unobserved heterogeneity given the random and noise. Okay. So we call it the variance of the random estimator. The random estimator, the variance. So what the theta is telling you is that, you know, we didn't want, technically, we didn't want the unobserved heterogeneity to be in the thing, to be in the composer. So the theta is telling you that variability that is coming from this unobserved heterogeneity inside the error. Okay, so when you look into the error, so in this case, this random effect is telling you that if you had not used a model called a random effect model, if you hadn't used it, then you would have left 62%, 64. You would have had 64% of the unobserved factors hidden inside the error. You will attribute them to the error 10, which you should not. So it's been able to fish it out in that regard. So this theta is very important. What is theta? Is it known or is not known? Is it known or is not known? Well, in practice, you don't know it. This theta is an important variable. Sometimes you can bring this formula in your journal. It's not known in real world, but it can be estimated. The same way the beta parameters are not known in the real world, can be estimated. In the wage data, most of the variations come from this unobserved factor. So the unobserved worker specific effect. Okay. This is good. This is good because it's helping us explain why on the time varying variables, okay, even though they were insignificant as you saw, the random effect lie closer to the fixed effect than the pooled OLS. Okay. In other words, if you get quite some unobserved worker specific effect or individual heterogeneity, what this means is that, oh, they were there, they would have caused a lot of problems in the pooled OLS. That's what it means. So the 64 means that the random effect estimator can be obtained from a transform model where 0.64 times, that is 64% times the individual mean is subtracted from the original data. So what this means is that you can perform the random effect model or estimator, you can perform it from the transformed model. And that you can only perform it because 64% of the information are contained in the unobserved factor. So the unobserved factor now makes it real, makes it sensible for you to do that. So a large fraction of the total variance is attributable to the data, this unknown value. The variation is attributed to this. In a random effect model, or in a random effect equation, the feasible GLS estimator will use the theta in place of the true value of the theta. Okay. And if you guys can remember feasible GLS, you can see that the omega was capped. So that is what it does, the same thing. When the value is 0, we know that we are in the pooled OLS, and when the value is 1, we know that we are in the fixed effect model. But in real life, okay, someone says, I don't understand the explanation. Okay, so what we mean is that, I don't know which one, but then I want to believe that you're talking about when I spoke about a cap and then one not a cap. Okay, now we told you that the theta is not known. The theta is not known in real world. Okay, so you got to explain which one you don't understand. Okay. Other than that, let me finish and then I will address your questions. Okay, the theta is not known, and because the theta is not known, we need to estimate it from somewhere. So whatever theta you are seeing there is estimated theta, not a true theta. Not a true theta, but it's estimated theta. And we've indicated that in real life, the theta is neither 0 or 1. It's in between the two. Because when it's 0, then we are back to pooled OLS. When it is 1, we are fixed at fixed effect model. Okay. All right. So let me wrap up this and answer all your questions. So this is a result of the panel model. You saw it in the R, and I'll reproduce it also here. Now, even though that is a random model result, you can, you remember I told you that the one that we did was, the transformation was Swami Arora's transformation. So you can use different other transformation. And if you want to change the transformation, you can rather use random method and change the transformation. And there are several other transformations. You can have the Amemiya transformation. This is the people that brought those transformations. Okay? You have there's a guy called Wallace and Hassan or something. Okay? 2 people. Walhu's transformation. You can use that one as well. There are several of the transformations you can use. Okay? But the standard one is the Swami's Arora transformation. If you want to use any transformation, read about it. Basically, read about it. You can have another transformation by Nelov. So that is also called Nelov's transformation. Okay. And you can add effects. You can add time specific effect. And I like this one, so I'm going to run this one. This one contains the 2 ways effect, okay, for fixed effect and run for time heterogeneity and for individual heterogeneity. This one. So you can include that and still have your Nelov, your transformation for Nelov and run that. And depending on which one you want to use. Now, I would encourage you as higher level student to go and read which one that will make sense for what. Okay. Instead of I'll tell you everything. So I'm going to just run this very one, the last one, even though you can do all of the rest. That's not even on it because I have them there. Oops. Well, you can run them on your own. This one, let me just show you. Because I'm supposed to copy the commands. Okay. I'm supposed to copy all of these commands and then go and run it. It will take time. Let me see. Let me go to my R and see. So copy and then do it on your own, okay? Because I'm more interested in the several tests. All right, so that is random effect. Now the next thing we're going to do is test you have to do to be able to correct, to select different tests to do when you have done your panel data econometric regression. Some of them are tests to determine whether you have to do pooled OLS. Some of them are tests to select between random effects and the principal. But then at this stage, I will wait for questions, and I will now go to the final part. After you've estimated the model, the test that one